Okay, so today we're going to be talking about, this is Mrs. Allen, and we're going to be speaking about 7-3 substitution with trigonometric identities, otherwise known as integrals with trig or trig integrals. So in this problem, in this section, we will be investigating integrals that look like those two forms, where it's their powers of sine and cosine together or powers of tangent and secant together. The key idea with these integrals is to use a u substitution. However, it will sometimes be unclear what u will be called. It's actually easier to select a choice for du first and then work backwards to find u. So once du is selected, the remaining integrals should be able to be rewritten in terms of u using the identities below. So really, it'll be important to make sure that you know your identities. You have two Pythagorean identities and two power reduction formulas. If you remember the double angles for cosine, you can obtain sine squared and cosine squared identities by manipulating the double angle identities for cosine, but we'll leave them at this right now. So those are the powers that we'll use. So the first problem that we'll be working on, and we'll be very consistent as a habit to say, when we have one of the powers, either or, sine or cosine, odd, generally what we do is we try to pair one of the cosine or sines off that are odd so that we have our du. So if you take a notice of this, that du is cosine x dx for problem number 1. And then if you look at this, then u is going to be sine x, right? So when we're kind of set up in this particular problem that you have your cosine x dx right away. So what happens here is this just becomes the integral of u squared du, which is then u cubed over 3 and plus c, but then we back substitute our u, so our answer becomes sine cubed x over 3 plus our c. That is the expression for the antiderivative of sine squared x cosine x dx. There we go. There you have it. There it is. Okay, so then now we're going to take it a step up, and we've got now the integral of sine squared cosine cubed. So again, at least one of the powers of sine x or cosine x are odd. So you can see that I'm going to pair one of the cosine cubed x off since it's odd, and I'm going to save one of them for the du. So if you look at what I have, I took the cosine cubed dx and I made it cosine squared cosine x dx. So this will be similar to the one we just did, because the du is still going to be cosine x dx. And then what I'm going to do is I'm going to change the expression so that you see where I have a sine. I need my u to be equal to sine x. So I need this cosine. I'm going to leave the du part with the cosine x dx, but I need the cosine squared to be in terms of sine squared. So now I have sine squared x, and then 1 minus sine squared x is what cosine squared is all about here. So this factor is really now that. So then we have cosine x dx on the end. So here we go. So we end up, and it kind of cleans up nicely, that we have a u squared times 1 minus u squared du, because cosine x dx is equal to du. So I now have the integral of u squared minus u to the 4th du. So I end up with the integral is equal to u cubed over 3 minus u to the 5th over 5 plus c. And then we're going to back substitute to get our answer. We're just going to say our answer is sine cubed x over 3 minus sine to the 5th x over 5. It's a 5 there. And then plus c. So there is the antiderivative. Okay. All right, move on to the next one. So we have both powers in this case are odd, so I can choose whichever one I want to. And since I chose cosine, du is equal to cosine, I'm going to switch it up here. I'm going to say du is equal to sine x dx. So my first move is I'm going to pair off one of the sines. So it's going to look like this. So now I have an integral that is the integral of sine to the fourth x cosine cubed x, and then I'm going to have a sine x dx here. So now when I choose my du to be sine x, you have to be careful. And for me, it's always been easier to put the negative sign with the u. It's a smaller, kind of more compact form. So I'm going to put the negative sign with the u on this one when I do my substitution. Okay? So now that I have my du ready to go, then I've got to change all my other expressions to cosines. So what I have here now is sine to the fourth. So sine to the fourth is equal to sine squared squared, right? So I know that sine squared squared is going to be 1 minus cosine squared, and then I'm going to square that, okay? So I've got 1 minus cosine squared x squared, and then I've got a cosine cubed x, and then I have the sine x dx. Okay. So now, again, you must be careful how you substitute in these expressions, because now my negative u is going to be cosine. So here we go. So now I'm switching over to u's, and so I have the quantity 1 minus a negative u squared squared times negative u cubed times du. Okay, so now in this is then going to be, this is really just going to be the same as plus u squared if you look at it like that. But we're going to be squaring this, so keep in mind that when you do square it, so and sometimes it's good to go, all right, what is 1 minus u squared squared in that case? And then we have times this. So then it's going to be 1 minus 2u squared plus u to the fourth, and then it's times negative u cubed. Let's do this really quickly. And so we have a negative u cubed plus 2u to the fifth. See, we're going to multiplying this through. And then that's going to be minus u to the seventh. Okay, take all this and scrunch it up. Okay, just a little scratch work over here. So our integral form then becomes, it's then the integral of negative u cubed plus 2u to the fifth minus u to the seventh. Now I did that kind of fast, so I want to double check this. Du. I think everything looks okay. All right, so now where do we go with this? We have then negative u to the fourth, where we're going to go ahead and take the antiderivative over 4. Plus, I've got a 2u to the sixth over 6. That's going to be u to the sixth over 3. Minus u to the 8th over 8. Okay, and then we have a plus c, arbitrary constant. And so now I've got to be careful, because now I've got to back substitute. And so I've got u's in here, but remember that it's easier if you think like this. I know that u is equal to negative cosine. So even though I use negative u's in here, u in the problem is negative cosine. So I'm going to go back and I'm going to put negative cosine in. You can see that this is not usually the preferred du. If I can use cosine as a du, it's a little bit easier because you don't have to worry about this negative in there. So then I'm going to say it's negative u, which is negative cosine x to the 4th over 4 plus negative cosine x to the 6th over 3. I might even leave the 2 6th power and over 6. I kind of like that, having the 6 in the denominator. There's a kind of a similarity between the terms then. And then we have minus negative cosine x to the 8th power, and that's then over 8 plus c. And now what I have to do is then straighten everything out. You can see what happens is that I have these even powers, so the signs are really not going to be affected. The last term is negative, the first term is negative. So each of the powers are going to be risen to an even power. So when we deal with this, we're just going to get the following. We're going to get negative cosine to the 4th x over 4 plus cosine to the 6th x over 3. And then, like I said, I could have 2 cosine to the 6th over 6. It's kind of nicer, I guess. And then you have minus cosine minus cosine to the 8th x over 8th, and then we have plus c. Okay, so getting a little long in the video, so I'm going to stop here, and I'm going to go on to case 2, where both sine x and cosine x are even. So again, this is trig integrals. In my title, I'm using substitution with trigonometric identities, often called trig integrals. Okay, I'll be back with part 2 of 7.3, substitution with trig identities.